We're given a vectored valued function r of t and asked to find parametric equations of a line tangent to r of t at the point 9, 3, negative 2 natural log 2. Let's begin by reviewing the parametric equations of a line in space. A line parallel to vector v with components a, b, c that passes through the point x sub 1, y sub 1, z sub 1 is given by the following parametric equations. So vector v is called the direction vector, where a, b, and c are the directional numbers. Because we want our line to be tangent to the curve given by the vectored valued function, we can use a tangent vector for our direction vector to find our directional numbers a, b, and c. But before we do this, let's begin by determining the value of t that would give us this point of tangency. We want to determine what value of t would make 4t to the third plus 5 equal to 9, which should be the same value of t that makes t squared plus 2t to the fourth equal to 3, which should be the same value of t that makes negative 2 natural log 2t equal to negative 2 natural log 2. So looking at the z component, notice how it's easy to see t would be equal to 1. But again, to emphasize this, let's go ahead and perform the substitution and find r of 1. So r of 1 would be equal to an x component of 4 times 1 to the third plus 5. The y component would be 1 to the second plus 2 times 1 to the fourth. And the z component would be negative 2 natural log 2 times 1. So again, notice how this vector does have the terminal point at the point of tangency, which would be 9, 3, negative 2 natural log 2. This is important because once we find r prime of t, we'll have to find r prime of 1 to find the tangent vector at that location. So now let's find r prime of t, which will give us our tangent vector. So for r prime of t, the x component would be the derivative of 4t to the third plus 5. With respect to t, that would be 12t squared. The y component would be the derivative of t squared plus 2t to the fourth. That would be 2t plus 8t to the third. The z component would be the derivative of negative 2 natural log 2t. We could use a log property to write this as a sum, but let's go ahead and find the derivative using the chain rule. So we'd have negative 2 times 1 over 2t times the derivative of 2t, which would be 2. Notice how this does simplify to just negative 2 divided by t. So again, r prime of t would have an x component of 12t squared, a y component of 2t plus 8t to the third, and a z component of negative 2 divided by t. And because we know the point of tangency occurs when t equals 1, to find our tangent vector, we'll now determine the vector r prime of 1. So r prime of 1, again, will be our direction vector for our tangent line. So we'd have an x component of 12 times 1 squared, a y component of 2 times 1 plus 8 times 1 to the third, and a z component of negative 2 divided by 1. So our tangent vector, r prime of 1, has an x component of 12, a y component of 10, and a z component of negative 2. Now we have all the information we need. Again, the point of tangency will give us x sub 1, y sub 1, and z sub 1, which we know is 9, 3, and negative 2 natural log 2. And the components of the tangent vector give us our directional numbers, which are a, b, and c. So a is 12, b is 10, and c is 2. Of course, these are not unique. We could use any scalar multiple of this vector for our directional numbers. So the parametric equation of the tangent line would be x of t equals 9 plus 12 times t, or 12t. Y of t would be equal to 3 plus 10 times t. and z of t would be equal to negative 2 natural log 2 minus 2t. Remember, parametric equations of a line are not unique, but these are probably the most obvious parametric equations for our tangent line. Let's go ahead and verify this graphically. So looking at our graph, this black curve is given by r of t, our vectored valued function. The point of tangency is this blue point here, and the red tangent line is graphed here in red. Notice how this does verify our answer is correct. And this purple vector here is the tangent vector which we used for our directional vector or for our directional numbers. I hope you found this helpful.